In this particular chapter of the electric charges and the fields, today we'll be covering these topics, which is Coulomb's law of electrostatic force and electric field and the flux. Okay, so these are the three important topics that we'll be covering. So according to our analysts, these are the very important topics which have been coming from this particular chapters. Now coming to the Coulomb's law of electrostatic force, it's an empirical relationship that is F is equal to force between the two charges. It will have the two types, obviously. Two charges will be there. One is a positive charge, another one is a negative charge. So the charge values will be there. The value of the charge is E is equal to 1.6 into 10 to the power of minus 19 coulombs here. So the force can be written as, and this is 1 by 4 pi epsilon naught into product of the charges, that is Q1 into Q2 by distance of separation between the charges. And charge can be written as an n into basic value of the charge, where n is an integer. This is the charge quantizations. So n can be the plus or minus 1, plus or minus 2, so plus or minus 3, so on like that it will be there. Okay. So this is the force, Coulombic force of attraction, for Coulombic force between the two charges. If they are the like charges, then there will be the repulsion, and if they are unlike charges, there will be an attractive force. This particular thing we know. So from this relation, that is F is equal to F is proportional to the product of the charges Q1 and Q2, and force will be inversely proportional to the square of the distance. So this is the basic thing where that we can have. So 1 by 4 pi epsilon naught value will be equal to the 9 into 10 to the power of 9 here, and epsilon naught value will be equal to the 8.85. Epsilon naught is equal to 8.85 into 10 to the power of minus 12 Coulomb square by Newton meter square. So this is the value of your epsilon naught conditions. So epsilon naught is nothing but a permittivity of the free space. If these two charges, or if the separation between the charges, that is the Q1 and another charge Q2, the space between them is been filled by another medium over here. Instead of the free space, if it is some other medium, then the force will be written as, and that is F is equal to 1 by 4 pi epsilon naught into product of the charges, okay, into r square. So now this is not going to be the epsilon naught. So this will be only the epsilon here, please. Fine. So this is the one where the medium is been changing from the free space to some other medium epsilon, or this epsilon can be, that is the permittivity of a medium, can be written as an epsilon r, that is the relative permittivity into epsilon naught. The relative permittivity can also be written as an k, which is called as an dielectric constant. Dielectric constant. Okay. Suppose if in this situation the force can be written as, and if I replace the epsilon with 1 by 4 pi epsilon r into epsilon naught into q1 q2 by r square. Now if the space between the q1 and the q2, both the charges, is partially filled with a dielectric like this of thickness t, and constant is going to be the k. So epsilon r, you can write it as a k, sir, and the total distance is r. So then what? How can you write this particular thing, or what will be the force now? So in this situation, you can apply this one as an 1 by, it will be the 4 pi epsilon naught into charges q1 q2 by, this is r minus thickness t plus t root k whole square. This is the force between these two things, please. So when dielectric is being introduced. So charges are this purely the multiples of the n value, that is an integers in this case, positive or negative integers here. So n is equal to plus 1 or minus 1 for the positive or negative charges conditions in this. Okay. So now if a body, if you remove some electrons from a body, it will be the positively charged body. If you add some electrons to a body, it will be a negatively charged body. Okay. So that is a issue, that is a relationship, please. So we know the charge value. This thing. So this Coulomb's law can only be applicable for point charges only. It is valid only for the point charges. That is, for the continuous distribution of the charges, we cannot apply, but we can apply with the small changes. For example, if I take a rod is here. On this rod, there is a total charge of capital Q is there, and there is another charge called as a small q, which is at a distance of r from here, and the length of the rod is going to be the L. Now, if the question is what is the force between the capital Q and the small q, but this Coulomb's law can only be applicable for the point charges. Here, it is a rod, so it's a continuously distributed charge. That is the length of the rod. Okay, no, so for the total length, the charge distribution is going to be the Q. So for these type of the questions, we need to consider an element over here. That is, consider a smallest portion in the rod, which is going to be an seems to be a particle. Then we can apply the Coulomb's law. Let the length of the part this element is going to be the dx, and the charge on the element is going to be the dq, and the dx is at a distance of x from the, or the distance between the elemental charge and the small charge q is x, and then in this case the df can be written as an 1 by 4 pi epsilon naught into charges dq into q by r x square. Okay. Now in this case, the unknown value is going to be your dq. So to find out the unknown value dq, let us write for the total charge is there for the length L, and dq is the charge for a length of dx. Then if we replace this one, q by L is into dx will be equal to the dq. Q by L is, we can also write the Q by L as linear charge density. And if I replace this one, df is equal to 1 by 4 pi epsilon naught into dq can be replaced here. That is total charge by total length. These two are constants into dx into charge q by x square. Now, if we integrate this one, then f is equal to take out all the constant values outside. So that will be the capital Q into small q by 4 pi epsilon naught into integral of 1 by x square into dx. So now we can integrate this one within the limits of, then the starting of the rod is, the starting of the rod from the small q is from the r, and the ending of the rod is L plus r. So integral of this one is going to substitute in the limits over here. So capital Q into small q by 4 pi epsilon naught. Substitute the limits in this one, minus 1 by x. This is r to L plus r. You can get what is the value of the force here, please. So in this way, we can apply the Coulomb's electrostatic force for the continuously distributed charges. Okay. So now coming to this one of the example on this particular thing, two small spheres, each of mass, how much they are? 10 milligrams are there, suspended from the point by a thread of 0.5 meters long. They are equally charged and repel each other. That means they are the like charges. Fine. So they are going to be equally charged and they repel each other to a distance of 0.2 meters. The charge on the each sphere, he has given that 8 by 21 into something here 10 to the power of minus 8 coulombs. So the value of the A. So in this one of the value should be either this one should be the A or this one. Okay, let's try to find out the case. Or else let's verify whether the given case is right or wrong. Okay, now coming to the question, two small spheres suspended from the single point. So I'll draw the diagram here, please. So this is the point when the point objects are being suspended. This is one, and this is your another one, which both of them are being separated by a distance of how much he has given here. These two are separated by the 0.2 meters. Okay, so both are having the equal charge Q and Q. So now why they are separating them basically? A electrostatic force might be acting on this one in this direction Fe, and downward force is going to be the mg. Since they are in the equilibrium conditions, the angle made by this particular point to this distance here will be same as this is theta or this is also theta, and here also the angle made with respect to the vertical will also be the theta. So to find out the electrostatic forces under it is under the equilibrium conditions. So how can we solve this particular relationship? Okay. So we can go for one thing, that is the tan theta. So tan theta is equal to what I can write, sir, here. Tan theta is equal to opposite side. That means this is exactly midpoint. So this will be the 0.1 meter. And the length of the string, the suspended threads of this length is 0.5 meters. Then we can get the adjacent side is going to be how much? So for that one, we'll be going for an sine theta terms, please. So sine theta is equal to your opposite side by 0.1 by 0.5. In that sense, sine theta will be 1 by 5. From that one, your tan theta can be written as an 1 by this or adjacent side. That will be root over 25 minus 1. That will be 24. How did you get this one, sir? This is nothing but the opposite side. This is hypotenuse. Tan theta is opposite side by adjacent side. Adjacent side is root over hypotenuse square minus 1 square. That is 25 minus 1 will be 24 tan theta. From this diagram, opposite side, which is Fe, adjacent side is going to be the mg, which is Fe by mg. You can write it. So Fe force because this is a tan theta value you do have. So 1 by root 24 into mg is equal to your Fe. So 1 by root over 24 into mass is 10 milligrams, 10 into for milli 1 10 power minus 3 grams, another 10 power minus 3, so total 10 power minus 6 kgs. G value 10 is equal to 1 by 4 pi epsilon naught. Since both of them are the same like charges, it will be q square by distance of separation between the both the charges is 0.2 whole square. So now on solving this one, this is 1 by root 24 into 10 to the power of minus 4 is equal to 9 into 10 to the power of 9 into charge q square by this I can write it as an 4 into 10 to the power of minus 2. Now take everything to the other side, please, and you can go for the solving. So that means your q square value will be 4 into 10 to the power of minus 15 by root 24 into your 9. So on solving this one, you should be getting your value of the q is going to be how much, and compare with the given values whether they are going to be right or wrong. You most probably you should be getting here 10 power minus 8 is the 10 power minus 15. You can rearrange this one to the 10 power minus 16 so that it can come down to the 10 power minus 8. So this is how you can find the charge. So this is one of the Coulombic force application that we have applied over here. Now coming to the another important one, which is called as an electric field here, please. So most of the questions will be running on this particular electric field. You have to be perfection in the formula of this particular thing, please. So you should be perfect on this particular for every formula of in this particular electric field. So how do you define an electric field? Basically, if you go, it is nothing but a field around a charge where its influence can be felt And electric field is a vector quantity, or it can be rather mathematically force acting on a unit positive charge, or this will be 1 by 4 pi epsilon naught into q by r square. This is the electric field vector conditions. So this r is the distance from the charge where you are finding the field value. From this one, you can also write electrostatic force can be written as an electric field into charge q naught. Okay, so these are the basic formulas of this one, and we have got the electric field also here. So now for any other conditions for the variable in the, if dq is going to be the variable, then electric field EVAR can be written as, and that is k into integral of some dq by r square, and you can solve it correspondingly, where it is nothing but the k is equal to 1 by 4 pi epsilon naught. Now the first one I'm writing here, so that is electric field of a long wire, that is infinitely long also you can go for it, which can be written as an E is equal to lambda by 2 pi epsilon naught r, where lambda is the linear charge density of this one, and it is the perpendicular distance r at the point P. So what is your lambda is called as a linear charge density. Okay. Now the second object, if I go, the electric field for an or of an a ring, if we can take, or rare ring. So continuously charged a distributed ring on its axis. For example, this is your ring. This is the along the axis at a particular distance called as some x from here. This is the point P. We are finding the electric field. So this is your radius R. Then on that sense, the electric field formula for this one can be written as an E is equal to 1 by 4 pi epsilon naught, or I can also write it as a K into, this will be the Q into, that is charge on this ring, into X by. So it can be written as an R square plus X square whole to the power of 3 by 2. So please be perfectible. Now it's a time you are going under the revision process. So we cannot go for the derivation thing, please. So and in the examination also you will be hardly getting a time to solve the sums for only 2 minutes. In those 2 minutes you cannot have go for the derivations, please. So you need to remember these formulas, please. Next one, third one. If I want to go for an electric field of a disk. So electric field of the disk can be of the same sort of a thing diagram along the axis. And this one, suppose if I go for the ring case only, I'm going back to the ring case. At x is equal to 0 means, that means E at the center. So E at the center will be 0, since 0 into this entire thing will become 0. Similarly, for the disk, you can write it as an E is equal to charge Q by 2 pi epsilon naught into r square of 1 minus x by root over, this will be the r square plus x square. Since this disk is an aerial object, then your surface charge density sigma can be written as a surface charge density sigma is equal to q by surface area of this one A. So that in that terms also you can write the same formula in terms of the sigma also. So if I write the same formula in terms of the sigma, this can be written as an sigma by 2 epsilon naught of 1 minus x by root over, that will be the r square plus x square. This is for a disk, electric field for a disk. Next one. So you do have the different objects in this particular electric field where we will be discussing them, please. So what are those different objects now? In this different objects we have seen till now, And wire or infinitely long wire, we have considered this one. Another one is going to be an ring. Another one is going to be the disk. So we'll be seeing another different objects for this one. For example, if I go for an or electric field condition only, so what will be the electric field for an sphere, solid sphere, if I go for that one? So E of a solid sphere or a conducting sphere, if I or else if I go for an instead of solid sphere, so E is equal to, that is 1 by 4 pi epsilon naught, that will be the q by small r square. This is for the conducting sphere. So for a conducting sphere, if this is the relationship electric field, so this is outside the things. So that means if you consider a sphere like this, I am considering a point which is outside the sphere, that the radius of the sphere is going to be the r. Here there is a point P which is at a distance of some smaller angles. Now if it comes to the on the sphere, so E on the sphere will be equal to the 1 by 4 pi epsilon naught into charge by, this will be the capital R square, since on the sphere means small r is equal to capital R. Now E inside will be 0 for a conducting sphere. So for all the conductors inside, the electric field inside will be equal to the 0. So next for a non-conducting sphere, so non-conducting sphere, the values of the outside, E outside will be same as this one, that is 1 by 4 pi epsilon naught into q by r square. Non-conducting in the sense it is a charged sphere where the charges will also be inside this one, inside the sphere. But for a conductor, charges will be only residing on the surface. That's a very important point you need to remember. So outside will be same as the normal sphere, and on the sphere also it will be same, which is equal to the 1 by 4 pi epsilon naught into q by capital R square. But coming to the inside, E inside, there will be a field which is 1 by 4 pi epsilon naught into q by capital R cube into small r. So where inside it will be proportional to the smaller. That means if I plot a graph for this one, the shape of the graph will be a straight line up to the value of small r is equal to capital R. After that, it will be a rectangular hyperbola E and R values. Okay, so this is the type of the graph that we'll be getting in this particular situation. You can also have the field due to the dipoles. So along the axial line or equatorial line, you can write it as an 1 by 4 pi epsilon naught into 1 by 4 pi epsilon naught. So on the axial line, it will be the 2p, where p is called as a dipole moment, dq on the axial line, and electric field on the equatorial line will be 1 by 4 pi epsilon naught of p by d cube. This is for an equatorial line, and this is for the axial line, ma'am. Okay, so these are the different types of the formulas or the relations that you can have it. So electric field inside a non-conducting can also be written as an rho by 3 epsilon naught into small r. Generally, this formula is regularly utilized. Fine, so these are the different concepts regarding the electric field. If we see the sum on this one, a uniform charge, uniform line charge of length L charge Q. So as shown in the figure, find out the electric weighted symmetrically arranged. That means it might be like this, for example, if it is an infinitely at this particular point, O, if this is your O, then symmetrical arranged conditions means this entire wire might be charged. So on that sense, what will be the electric field here? E is equal to, it will be 1 by 4 pi epsilon naught into lambda can be written as an Q by L, that is R square into L. You can conclude this particular thing electric field. Just now we have written this particular formula, but in the different format I have written E is equal to lambda by 2 pi epsilon naught R. In this format, it has been written on lambda by 2 pi epsilon naught r. Got it? So you can also write this one in those terms also, please. So this will be E is equal to lambda by 2 pi epsilon naught r. So length of the current is going to be the L. Fine. So now we have replaced this one. So we don't know at which particular point it is the finite length or anything, or if it is the point, then the electric field are going to be in the two components. One is going to be in the horizontal EX, another one will be in the vertical down. It can be vertically downward or it can be vertically upward. So net moment, net electric field in this direction will be obviously zero. So this is the one he has been asking us to calculate, sir. So you need to substitute all the values. So here the missing thing is going to be shown in the figure. If figure might be there, then you can do it comfortably. Okay. So this is, but for the line charge or for this particular length, the formula you have to use is E is equal to lambda by 2 pi epsilon naught r. Fine. Now coming to the another important topic and interesting, that is called as an electric flux. What do you mean by electric flux? Electric flux is nothing but a number of lines passing through an unit area. Number of electric lines passing through a given area, or according to the Gauss law, electric flux can be written as an integral b bar dot dx, b bar dot des. You can write, and this is equal to q by epsilon naught, or charge enclosed in a closed loop. Okay, and this one we call it as an Gauss law. This one is called as an Gauss law. So this is how you apply the things, please, for the different objects. Okay. So most important thing, this is you called as your flux dana. So how can you find the electric field because of a wire from this one? Suppose a wire is here. So if electric field is in which direction it is being. So it's a line charge is there, totally charged distribution is there, perpendicular to this one, there is an electric field E bar. Fine. So then what will be in this case? So substitute the value of the electric field in this one. Integral around a closed loop E dot into ds. That means what is the current loop around this loop is? In this loop, you have to write whose radius is something r is equal to charge inside this loop into epsilon naught. So E can be written as an into surface area. What is the surface area here? That is 2 pi r into some length L is equal to charge on the wire. That is lambda L into lambda by. So L terms will be cancelled. So the same formula that we have written 1 by 4 pi epsilon naught, or lambda by 2 pi epsilon naught into r. So this is how you can derive the same formula using the Gauss law, that is lambda by 2 pi epsilon naught into small r. Fine, Anna. So this is another very, very important formula on the flux, please. Right, so please be careful of this one. So these are the electric flux conditions. Next one. So he is asking the charged particle of charge Q. A charged particle of charge Q is placed on one of the corner of the side A. Find the flux through the shaded area, he is asking. Suppose if a charged particle is inside the cube, exactly at the center, then charge or the flux passing through each side will be, if the charge is exactly at the center Q, then total flux interval in a total flux is equal to, according to the definition, Q by epsilon naught should be happen. Since the cube is having the six sides, it should be the Q by 6 epsilon naught. So any one of the side, this will be the flux due to any one side is equal to Q by epsilon naught. Okay, so the Q by 6 epsilon naught, any one side or one phase, you can call it as. Now In this one, he is asking what is the flux through only the shaded region. From the entire square, from this entire square, if this much flux is being released, then the shaded region is half of the square. Right, sir? A shaded region is half of square. That means flux through this one should be half of this one. So those types. So this is the one half. This is another half. Okay, now. So sorry here. I've just done a mistake here. So how many sides will be there for this particular cube? 8 sides. So 8 epsilon naught for each one. 8 epsilon naught for the each side. And in that one, only half is been coming through the shaded region. So then it would be the how much it should be, sir? Q by 8 epsilon naught half is been emerging from this side. So how much it will be? The Q by 16 epsilon naught, right, sir? Then what will be he is asking total shaded region will be how much? So that means from this region, he is asking the case. Can I do that exactly half of the square, sir, please? Okay, you might have not confused here. Okay, anyone, any hints, please? Right. So the here, this value I have got when the charge is at the center of the cube, sir. But in this question, the charge is located at the corner of the cube. That means if you can construct like this, another cubes, so how many cubes will be required to take this charge to exactly the center? So then top two cubes, on the other side top two four, and total 8 cubes. Then, so keep it aside, sir. Now coming to this question, please. So total there will be 8 cubes. Now charge is exactly at the center. Now the flux through each cube will be total flux is q by epsilon naught according to the Gauss-law. 8 cubes are there. From each cube it will be q by 8 epsilon naught. From each cube, q by 8 epsilon naught, how many phases will be exposed outside? First phase, this will be second phase, this is only 3 phases will be exposed outside. That means flux through each phase will be 1/3 of q by 8 epsilon naught, which is q by 24 epsilon naught. Okay, this is the one which is coming through each phase. So the shaded region is half of the one phase, and this another shaded region is also half of. Then this half plus this half will give you the complete full phase. Then your answer should be q by 24 epsilon naught. So these type of the questions will be asked in this particular thing, please. So these are all these questions are the previously asked questions, please. So lot of these type of the quantitative, logical, or the reasoning ability questions are there in the on the RISE platform. You can utilize it by getting the subscription, and you can also get the discount by using the code JJ10. Now questions based on the system. So these questions actually for you people to solve them. So I'll go ahead with this one. Infinite number of the point charges are there, each carrying how much charge, sir? 1 coulomb, 1 microcoulomb are placed on the y-axis 1 comma 2 comma 4 comma 8. The total force on the 1 coulomb point charge placed at the origin. Okay, so the value of the x is going to be how much? Now for our convenience, I'm taking the y-axis on along the horizontal direction. Let this be your y value, y-axis. At the origin, you have got a charge of 1 coulomb, and at every point you have got a charges of the 1 microcoulomb at what distance? 1 meter. And 2 microcoulombs is at what distance? 2 meters. And 3 microcoulomb will be at which distance? Sorry. 1, 2, and 4 microcoulomb is at which distance? It is at a distance of how much, sir? 4 meters. That is third charge. Is at a distance of 4 meters from here. So all the charge values are 1 microcoulomb. This is also 1 microcoulomb. So 1 microcoulomb. This is the distance. So if we apply the force equation independently, that is force between the first one and the origin, that is F1 bar plus force between the second one and origin F2, force between the third one and this one F3. So since all of them are the vectors, all the forces are going to be acting in the same direction. If all the forces are acting in the same direction, then go for the vectorial representation summation of these things. What will be the force formula for the first one? 1 by 4 pi epsilon naught into the charges, please. One is 1 coulomb, another one is 1 microcoulomb. That is 1 into 10 to the power of minus 6 by distance of separation is how much, sir? 1 meter, that is 1 square. Similarly, 1 by 4 pi epsilon naught into 1 by 4 pi epsilon naught into second one also 1 by 1 into 10 to the power of minus 6 microcoulombs. And the charge, another charge at the center is going to be the 1 coulomb but the distance has been come down to the 2 meters, which will be 2 square. So like that, you need to write this, all the values will be there. And finally, last one. If you take common all of them, what will be there, sir? 1 by 4 pi epsilon naught 10 to the power of minus 6 for the micro. This also constant in both the cases, please. Next, if I go into the bracket, this is 1 plus 1 by 4. 2 square will be 1 by 4 or so on like that. 2 square 1 by 4 plus next one 1 by 4 square 16. Next 1 by 8 square 64 plus so on like that. Is it not GP, sir? Apply the geometrical progression value and solve this one. There your 1 by 4 pi epsilon naught 9 into 10 to the power of 9 into, that is 10 to the power of 6 into, what will be the infinite series? 1 by 1 plus 1 by 4. And go ahead for the solving. You should be getting your answer correspondingly. Right? Next one, sir. A solid sphere of the conducting radius r has a spherical cavity of radius a. At its center, a charge plus q is kept at the center. The charge at the inner face. So, what will be the charge at the inner face? This is a sphere. There is a cavity at the center. You have placed a plus q at the center. Then minus q has to be induced at the center. Electric field is equal to 0. Outside these two things, there should be the plus q. Now, if I write what he is asking, sir, charge on the inner surface and outer surface position. Inner surface is minus q. Outer surface is plus q. Okay. So, for which option you can go, sir? Inner surface is going to be the minus q, outer surface will be plus q. Now the smaller distance in between these two things, and here there is a conductor. At conductor, electric field will be equal to 0. Just now we have discussed that. So all the three options for this is the minus q, plus q, and 0. Two conducting charged particles of negligible volume whose charges are 21 nanocoulombs and minus 1 nanocoulombs respectively are brought in contact and separated by a distance of 0.5. When these two spheres are brought in contact, what will happen to the total charge? Total charge Q is equal to Q1 plus Q2. Q1 is 21 into or 2.1 into 10 to the power of minus. How you should write this one, sir, please? Any idea? You have to add these two charges. 2.1. What is this one? Nanocoulombs. What nanocoulombs means what? 2.1 into 10 to the power of minus 9 plus minus 0.1 into 10 to the power of minus 9 for the negative charge. So on the whole, it will be the 2.1 minus 0.1 whole to the power of 10 to the power of minus 9. So from this one, the total charge becomes 2 nanocoulombs. Now, when you separate the two identical, two conducting spheres charged by negligible volume. Now, when you're separating them, then on both the spheres, since their spheres are identical, force will be the same. But how much distance you are separating them? 0.5 meters is asking the force. F is equal to 1 by 4 pi epsilon naught. Charges. What are the charges between them is? One charge is how much term? Q1. 2.1 into 10 to the power of minus 9. Another charge is, or you can substitute the total charge here instead of this, where you can write it as a total charge Q1 to Q1 into Q2, that is 2 into 10 to the power of minus 9 nanocoulombs by distance of separation is 0.5 whole square. Okay, so on solving this one, you should be getting your answer as this is the solvent. Got it? So these are the types of the questions that can be asked in your examinations, please. In your final examinations, please be careful, Nana. A point charge plus cube, 12 microcoulombs, is at a distance of 6 centimeters from the center of a cube, of a square. That means if I construct an imaginary cube like this, there will be an cube in this way. Okay, that means to the side 12, C 6 centimeters should be exactly at the center. That means charge Q is placed at the center. Electric flux is asking what is the formula then? Total flux phi is equal to, it will be the Q by epsilon naught. Total charge is how much? That is 12 microcoulombs, 12 into 10 to the power of minus 6 by epsilon naught. 8.85 into 10 to the power of 10 to the power of minus 12, and you can solve this one to get the value of the phi is going to be how much. Got it? So this is the one of the important things, please. So now go through them, go through this chapter of every formula and try to acquire all the formulas, try to read all the formulas, please. So the formulas has to be on your fingertips. It's a very, very important in this particular chapter. So please be careful of this one. So now I'm just closing this session. All the best.